Welcome, everybody, to our third series of our Heliophysics workshop series. It is great I see some returning participants, so I'm glad that you are just soaking in all of this knowledge. As I've said in the previous workshops, this is a little bit different than what we typically do at StarNet. This isn't necessarily a professional development workshop, but it's an opportunity for you to hear what some great scientists are doing in terms of solar science, heliophysics, and just celebrating the year of heliophysics this year. So today we are joined by Vincent Ledvina, or you can call him the Aurora Guy. He'll tell you a little bit about how he got that cool nickname, to learn about the science of the aurora and also ways you can get involved with your library and your community. So with that, I'm going to turn it over to Vincent and we'll begin.
All right. Thank you, Claire, for that introduction. I appreciate it. Hello, everyone. My name is Vincent Ledvina. I am a second-year PhD student at the University of Alaska Fairbanks, and I am studying the aurora, and in particular ways that aurora chasers and the general public can get involved in research in collaboration with scientists. So I'm really excited to talk with you all about that today. So let's get started. So first, I'll kind of tell you a little bit about my story. And again, this Aurora Guy nickname, how I came to be known as that. Then I'll get into a little bit about the science behind the aurora, space weather, and I think most excitingly, what is this thing called citizen science and how are aurora chasers and everyday people really making real discoveries and real advances in our field. And then finally, I'll just go over some activities that you may want to do with your patrons, with your library guests, that kind of center around this idea of the public getting involved in research and learning more about the aurora. So here's my aurora origin story. I saw my first aurora when I was 4 years old in 2003. So I grew up in the Twin Cities in Minnesota, and I saw the aurora while I was trick-or-treating coming back home after a long night, and it was just an amazing sight. I just, I have a vivid memory of that, even though I was only 4 years old. And, obviously I didn't go to grad school when I was four, but I think that that experience really embedded this latent passion or this really, just great interest in the natural world that has been with me ever since. So I joined Scouts. I was a Cub Scout and then later a Boy Scout, and achieved the rank of Eagle Scout when I was 16, and that really, more or less forced me to be outdoors all the time. I mean, I loved it, but I did a lot of camping and learned a lot of things about survival skills and all that stuff. But I think from that time, I got a lot of experience and a lot of time underneath the night sky in Minnesota, which is just fantastic and just beautiful. I became interested in photography, particularly astrophotography. I discovered about, photographing the northern lights in the night sky. And I think that that's really the pinnacle of this genre of photography because the Milky Way doesn't really change from night to night. But the aurora is something that you have to forecast, you have to catch. It's like storm chasing, but the space kind. So I thought this was a really fun challenge. I took my first aurora photo when I was 16 and I was hooked. So I wanted to actually move to Alaska right away, but my parents said, nope, that's too far from Minnesota. We want you a little closer to home. So I moved to North Dakota to study physics at the University of North Dakota. This is kind of where I got this Aurora Guy name. And I wasn't really into social media at the time. I am now. But I started posting these photos on Instagram. And one time, the University of North Dakota shared my photo and it, quote unquote, went viral. It was the most liked photo that they had ever shared on their page. And one weekend, I just got all these people coming up to me on campus. Somehow they recognized me and asked me if I was, quote unquote, that Aurora Guy. And at first, I was like, I don't know about that. I just take Aurora photos. But then my friends said, no, you are the Aurora Guy. Just run with it. So that's who I am now. And really, it's true. I mean, everything I do kind of revolves around the aurora. I'm still an aurora chaser. I go out all the time in Alaska and photograph the night sky and the northern lights up here. And I just love it. So here are some adventures I've had over the past few years. I actually took a gap year in 2022. So I graduated with my undergrad with my bachelor's in physics from UND in 2022. And I took a year just to sort of enjoy life after, getting a physics degree is kind of stressful. So I took a year off and I did a lot of aurora chasing. I met a lot of great people through social media, through Instagram, and went with them on a lot of trips. So this was one of these trips to Churchill, Manitoba. I suggest you put that into Google Maps and find out where that is because it's very remote. It's on the Hudson Bay in northern Manitoba. You can only get there via a train, which is 20 hours from the nearest drivable town, or 40 hours from Winnipeg. There's polar bears as well. So it's just an extreme location. This was in March of 2022. And then I went back in September and actually saw polar bears. That was kind of the time to be there for the bears. And it's a pretty humbling, maybe a little bit scary experience being out in the dark and potentially being stalked by a polar bear. So we saw a lot of them, and thankfully only one at night. But they were out during the day for sure. So that was a really fun time. I saw some amazing auroras, and then actually the same year in March, I was fortunate enough and privileged enough to have been involved in the sounding rocket campaign called LAMP, or Lost Through Auroral Microburst Pulsations. And this was when I was an undergrad student. So what ended up happening is just somebody who I was working for at NASA earlier. Her name is Dr. Liz McDonald. She got an email from somebody at asked if she knew any students who'd be interested in helping out with this sounding rocket because all the other grad students were busy on another campaign. So I was asked if I wanted to help out. I was in North Dakota. It was a Tuesday afternoon. I emailed all my professors and I said, hey, I know midterms are next week, but I really want to do this thing. They all got back to me within the day, and I was on a plane Friday morning to Alaska. So it was a really last minute decision. I saw the best aurora of my life on March 5th, 2022, actually the same night that we launched the rocket, and that changed my life. It was just awe-inspiring, amazing, and just, it was, I don't know, I don't have any other words to describe it. It was just phenomenal. So that really solidified my decision to move to Alaska, and that was my first high latitude aurora experience. And now I'm a space physics PhD student up at UAF. I'm actually living in a town called North Pole, Alaska. And, people always ask me if that's a real thing. Yes, there is a town called North Pole. I really like to share my love for the aurora. I think it's not only beautiful, but something that a lot of people can, it's one of those things where you learn about it in the textbooks and you see it online and you learn about the science, and the science itself is cool, but you can actually go out and experience it firsthand. I think that that's really cool and powerful. I'm a photographer. I love taking photos, capturing the night sky, capturing the beauty of the aurora and sharing it with others. I'm a citizen scientist, so I like taking my photos and potentially using them for research if possible. And that research includes things like auroral beads, which are like strings of pearls of aurora that you can see in the sky, which is what my PhD thesis will be about. So now I want to open up a poll to see if you all saw the aurora this year, because this was a great year for aurora chasing. So I think we just open up a poll there, either answer yes or no. Nice, I'm seeing lots of yeses. Okay. And yeah, 2024 was an amazing year to be an aurora chaser, an amazing year for the aurora borealis and the aurora australis as well. We had tons of great activity. We had two major storms. We had one in May and one in October, where auroras were seen around the world, including all 50 US states, which is amazing. Here's what it looked like on October 10th. This is a map of the world, and all these little blue dots are where people reported seeing the aurora. And this data set actually comes from social media. So one of my friends went on social media and just simply asked the question, did you see the aurora last night? And people who responded yes, he logged their location and the time at which they saw the aurora. And I took that data and I said, hey, wouldn't it be really cool to see over time, all these reports plotted out? And you can almost imagine, as it gets dark over the US, all these people, reporting the aurora and seeing it for the first time and just being amazed. And so why is this happening? Why are we seeing all the auroras this year? Well, right now the sun is going through what is called its solar maximum phase. So the sun goes through a solar cycle where every 11 years it goes through a solar minimum and then a solar maximum. So every 11 years is a solar minimum, every 11 years is a solar maximum. And it's kind of like a winter and a summer season on the sun. When it's the summer, the sun is more active or solar maximum. There's a higher activity of space weather, of things that can cause more auroral storms. And right now we're in the midst of that solar maximum, which started around maybe 2022 and will last hopefully another couple of years until we start descending down into solar minimum. And the auroras don't disappear at solar minimum. You just don't get as many of those frequent large auroral storms, large space weather events where you can see auroras all across the US like we have this year. So now what causes the aurora? Well, it all has to do with the sun. Everything's connected to the sun. The sun gives Earth energy. This energy helps drive things like weather, life, and even the aurora. It's all tied to space weather. So like we have weather on the ground, we have rain, we have clouds, we have wind. We have the same in outer space called space weather. And the technical definition is space weather referring to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. But really, space weather can be boiled down into the aurora. I think the aurora is the perfect phenomenon that really encapsulates the sun-earth connection. It's a manifestation of everything going on. You can look up in the sky and understand so much about what's going on in outer space by just looking at the aurora dancing above. It really is cool. But it's also more than just the aurora. There's so much to do with space weather. It's like thinking about terrestrial weather and only focusing on a tornado. There's so much more. There's windstorms, there's clouds, there's rainbows, just like in space weather. Auroras, shock waves, giants in space. There's the sun. There's solar flares. There's incredible space missions. This entire field, I think, just doesn't get enough attention because it largely is invisible, all the stuff in space. But the aurora is that visual manifestation of everything going on from the sun to the earth. So just like the sun creates weather on Earth, it creates weather in space too. And yep, it's all because of the sun. So a lot of this activity and something that is really important to understand is that there's a wind constantly blowing out from the sun called the solar wind. It's changing every minute, hour, and day. That's sort of the definition of weather. And I always make the analogy that the sun is like a hot cup of coffee. And the hot liquid in the cup of coffee, we've all drank, a hot cup of coffee, and you notice the steam coming off the top of the cup, right? The steam is kind of like the solar wind, except for the sun, is a burning ball of gas and plasma instead of a hot liquid. But that wind is blowing out, and it's because the sun's atmosphere is so hot, it's expanding super fast, and the sun's gravity can't hold it in. So there's this constant sort of stream of charged particles like protons and electrons and magnetic fields that get blown out into space, into the solar system, and it hits everything. It envelops everything in the solar system, including the planets, moons, asteroids, spacecraft. And this solar wind is full of magnetic fields and electricity. Usually it blows pretty calm and gentle, but sometimes with severe space weather, you can get fast gusts of solar wind, which we call coronal mass ejections, big bursts of plasma and energy from the sun, or really fast streams of solar wind. And luckily, the solar wind doesn't just hit Earth and penetrate all the way down to the surface. We have an atmosphere, and more importantly, a magnetic field inside of our Earth that extends out into outer space, forming a protective shield called the magnetosphere, which sort of acts like a force field or a protective bubble, shielding us from the brunt of the sun's solar wind. So when the solar wind hits our bubble, some of the electricity that's coursing through this wind does make it through and sort of penetrates over the weak points of our magnetic field, which are over the poles. Like if you've ever taken a bar magnet underneath a sheet of paper and you notice like the field lines and you put some iron filings on the top of that paper, you notice the field lines being traced out. Those 2 points over the north and the south poles are kind of where all the energy can get funneled. So some of the energy from the solar wind does make it through over Earth's polar regions, but most of it gets diverted around and sort of like a rock in a stream of water. It forms this magnetic bubble, instead of just being a perfect sphere, forms kind of like a teardrop shape, which is what our magnetosphere looks like in outer space, this sort of teardrop of protective magnetic field that shields us from the potentially harmful solar wind. And so then how is the aurora created? What is the aurora? Well, in essence, it is nature's most beautiful light show. And it's formed the same way that a neon lamp works. But instead of electricity coming from a wall outlet, it comes from outer space. Charged particles from space through the solar wind penetrate down into our magnetosphere. They get channeled along Earth's magnetic field lines and eventually precipitate, just like rain does from clouds, from space into Earth's atmosphere. And this particle precipitation, these particles come in with a certain amount of energy, and just like a game of Plinko, they start hitting gases on their way down, trying to make it to the surface. As they interact with more and more gases, they lose energy and eventually fizzle out. So none of the auroral particles actually make it to the surface. But when they interact with these gases in our own atmosphere, including oxygen and nitrogen, they give off certain colors in specific wavelengths of light. So you can see here on the right, this diagram, oxygen above 120 miles will glow red. And then below that is the same oxygen, just at a little bit of a thicker density. And a combination of nitrogen and oxygen creates a blue and a green particle. And then below that, a layer of diatomic nitrogen, or N2, produces sort of this purpley emission when these particles from outer space penetrate even further down below 60 miles. So this pink emission only happens when the aurora is really strong, when those particles have enough energy to make it to those lower altitudes. And this is all happening in a layer of the atmosphere that we call the ionosphere. So ions referring to the fact that this layer is mostly charged. So if we go back here, these particles up here, these oxygens and nitrogens, they aren't the normal gases that we breathe here on the ground. We breathe O2 and N2, but up at higher altitudes, there's just not as much force holding those two atoms together, so they dissociate into their ionic forms. And that's how they're able to produce light, is that electrons raining down from outer space are able to sort of chemically combine and interact with these other charged particles in our own atmosphere and create the light. And what's important to note here is that the ionosphere is very high up in altitude. We're talking, potentially 15 to 50 times higher than a plane flies. I mean, a plane is all the way down here. You can barely see it. Here's Mount Everest, for example, or your tallest storm clouds. And the auroras are taking place in an area that occupies, first of all, a large amount of altitude. That's why the auroras can appear so tall and appear very, you can see them from very far away because they're so high up. But also, to chase the aurora, to see the aurora, you have to have clear skies. All the clouds that we see on the ground are sort of in this tropospheric layer. And the aurora is happening many, many times higher than that. So the aurora is like a giant neon lamp in the sky, and I used AI to make this. I think it did a pretty good job. So the same way that a neon lamp works, you have electricity flowing in, energizing a gas, and producing light. It's the same way that the aurora is created. And so you can see the aurora in a number of different methods. The most reliable way to see the aurora is to travel to a place under the auroral ovals. So the aurora, these particles, like I said, kind of funnel down over Earth's magnetic weak points, over the geomagnetic poles. And the pattern that they create is that of an oval around these geomagnetic poles that we call the auroral ovals. In these auroral ovals, you'll see the aurora every single night. It's clear and dark. So that means that regardless of how fast the solar wind is blowing, regardless of how strong the space weather is, even if it's really, really quiet, very low activity, you will get auroras in those auroral ovals. And these ovals, they're usually pretty thin and narrow. And that means that you can only see aurora when you're underneath them. But during geomagnetic storms, they can expand, they can grow wider and extend to lower latitudes, which means you could potentially see aurora in your own backyard. And so this happens when the sun gets angry. These gentle breezes of space weather can turn into giant storms. And I mentioned this earlier, but the sun can let out these sort of big sneezes of particles called coronal mass ejections. You can actually see that here in this red sort of image, this red colored GIF here. This is actually an artificial eclipse in space by a spacecraft blocking out the bright sun so we can see all the particles coming off the sides. You can see this big explosion, this big loop of plasma coming off the sun. And luckily, this wasn't directed at Earth. If it was directed at Earth, you would see kind of an expanding halo around this disk. And these sneezes can reach Earth in around 1 to 3 days, so much faster than normal solar wind, which usually takes 4 to 6 days to get to us. And when they come close to our planet, when they butt up against something called some of the energy within the CME can couple with Earth's own magnetic field, and energy can penetrate down over the weak points, over Earth's geomagnetic poles, and flow into the atmosphere through electrons precipitating down, interacting with gases, causing the aurora, like I just explained. And space weather could affect you. Not only does space weather create the beautiful aurora borealis and aurora australis. Aurora borealis is in the northern hemisphere, aurora australis is in the southern hemisphere. But space weather can also cause damaging effects for assets on the ground, including power grids, even farmers and their tractors could be affected by space weather disrupting communications between the ground and in space. And of course, in space, we're not protected by Earth's atmosphere, which block a lot of these auroral particles. So you can have these electrons, these high energy particles directly impacting satellites, which can cause charging, damaging electronics. Or if you have people in space, either on the ISS or potentially on an EVA, like actually in outer space, this radiation could be damaging. And now we want to go back to the moon, which is actually orbiting outside of Earth's protective bubble. So you don't even have the protection of Earth's own when these space weather events happen. So space weather is something that we're watching really closely all the time. People looking at the sun, monitoring the solar wind and how strong it gets 24/7. So it's really important, not only for auroral scientists and auroral physicists, but really the everyday person to know about space weather, because if it gets severe enough, it could potentially affect you. And one such case of one of these extreme events was the Carrington event, which occurred in 1859, and before any of us were born. But in 1859, we didn't have a whole lot of modern technology. 150 years ago, 170 years ago, we didn't have much going on except for telegraphs, but all the telegraphs at the time were affected. So if this happened today, scientists wonder what the effects would be. Obviously, our modern day society is much more dependent on the technology than we were in 1859. And what occurred is we had a really strong coronal mass ejection, a really big gust of solar wind. And actually, Richard Carrington was looking at the sun through his telescope and observed one of these flares, these solar flares that typically create these big coronal mass ejections. He observed one of these flares in his telescope, and then less than a day later, we saw auroras just erupt all over the world, almost seen down to the equator, in fact, which is just crazy to think. And the effects on the ground were that all the currents, all the electrical currents in the atmosphere, just due to simple laws in basically electrodynamics, electromagnetism, if you have a time varying or a changing magnetic field, you can induce a current in the ground. So in the atmosphere, there were lots of auroras going on, and that induced what are called geomagnetically induced currents in the ground, which traveled up through telegraph wires. There was so much energy in the ground, in the air from the aurora, that operators could unplug their telegraph systems and continue sending messages. They could do that without any power attached. And this was fun for a while until they would start tapping their Morse code, and sparks would start flying out, lighting paper on fire, and actually a lot of telegraph stations around the US burned down. So the Carrington event is perhaps the most infamous space weather event, and remains a constant reminder that the sun, even though it can give us beautiful auroras, can also cause potentially devastating damage to modern technology. So now, taking a little bit of a shift here, I want to talk about citizen science. And before I begin, I just want to say the word citizen is not necessarily a requirement to do citizen science. The sort of shift in the field now is to start calling this participatory or community science, because you don't have to be a US citizen to take part. But I'm going to be talking about citizen science and using the word citizen just because it's something that I'm familiar with. But just know that the term citizen science is changing. The definition is organized research in which members of the public engage in the processes of scientific investigations by asking questions, collecting data, and or interpreting results. And citizen science looks like a lot of different things. So you may have heard of something called Zooniverse, or you may have heard of iNaturalist or Merlin, or any of these citizen science projects, people interacting with their natural environment, recording what they see, and that data being used by scientists. That's sort of how citizen science looks in a majority of aspects. But it can also be educators collaborating with scientists in the classroom. It can be people out photographing the aurora and then noticing strange things in the sky, talking to scientists later. Citizen science is a very wide field and encompasses a lot of different things and very exciting. The public can actually become engaged in real research and make a real difference in the scientific community. And Aurora chasers are part of this citizen science movement. And citizen science has been around for hundreds, if not thousands of years. But just until recently, really, we haven't known about many of these phenomena, such as Steve, fragmented aurora-like emissions, red aurora with green diffuse arc, these different types of aurora, because citizen science and the aurora science community is fairly new and still in its infancy. So it's really exciting because just within the past 10 years, aurora chasers have become involved, and yeah, it's definitely a new field. It's very there's always late breaking and groundbreaking research being done, and aurora chasers have all had a hand in learning more about these rarer types of aurora because they're always out looking and recording these auroras with their cameras, and those data can be very useful to scientists. So one such example of a rare aurora that was discovered or helped being discovered by citizen scientists is something called STEVE. It stands for Strong Thermal Emission Velocity Enhancement. And it's somewhat incorrect to say discovered by citizen scientists because, like every aurora or auroral phenomenon, these things have existed for as long as Earth has had a magnetic field and as long as we've had an atmosphere and a solar wind to create this sort of interaction which creates the aurora. So Steve has been around for a long time. Carl Stormer actually photographed Steve in 1911, but didn't know what it was and obviously didn't call it Steve. He said it was a feeble, homogeneous arc of great altitude. Much more kind of proper sounding than Steve, but I personally like Steve. So starting in around 2018, so a lot of this comes about because cameras have been getting better over the past 2 decades, obviously, right? Especially in smartphones, but in sort of like the professional photography community, the amount and how pricey these really good cameras are, it's basically created this, this phenomenon where the everyday person can afford one of these cameras that can record the aurora in a really, really unique and really powerful way. I mean, you can grab $1,000 camera now and take images that are better in some cases than science grade imagers can capture. So this kind of all culminated in 2018. Aurora chasers started noticing this weird streak in the sky. And usually when you're looking at the aurora, this was actually in Alberta, the Alberta aurora chasing community kind of led this effort. But usually when you're looking at the aurora, especially if you're not underneath the auroral oval, it'll appear, in the horizon. But they started noticing this strange arc that was appearing overhead, this white/mauve arc. And they didn't know what it was, but they looked at the literature and said that it most resembled what's called a proton arc. So they went to scientists and they said, hey, we're seeing this proton arc and it's really cool. Here are some pictures. And the scientists said, wow, those are really cool pictures, but that's not a proton arc. That's something that we've never seen before. And so the citizen scientists, the aurora chaser, said, wow, okay, that's really cool. What is it called? What is the name for this? And the scientists said, we don't know what it's called. We don't have a name for it yet. So if you've ever seen the movie Over the Hedge, you'll know where Steve came from. But essentially in the movie, you have all these backyard sort of park animals like a squirrel and a turtle, and everything over the hedge is this sort of, it's like the new development coming in, threatening to destroy their habitat. And they're really scared about this, all the humans over the hedge. And in order to make it sound less scary, they start naming it Steve. They start referring to it as Steve. So it's kind of a funny way of making this weird aurora, this new type of aurora, seem a little bit more familiar and approachable. So the name stuck. NASA said, okay, you can have your Steve, but we're going to call it Strong Thermal Emission Velocity Enhancement. So it's actually not a normal aurora. Normal aurora is produced by electrons or charged particles coming in, streaming into the atmosphere, riding along magnetic field lines like surfers, penetrating the atmosphere, colliding with all those gas molecules like I was talking about before. But Steve is actually this really hot river of gas that almost stretches around the entire world. and usually occurs right after geomagnetic, what are called substorms. So the aurora flares up, it gets really bright, and then it starts cooling down. The super starts to form. It gets really hot, and the air flows really fast, so fast that it glows white hot. So that's why Steve looks white and is not green. It's like you heated up a metal object and it starts glowing red or white hot. So citizen scientists were very instrumental in discovering this phenomenon called Steve, and continue to be instrumental and key players in discovering and characterizing other rare auroral forms. So now I want to transition into how you or people who visit your libraries can contribute to aurora science, because really you don't even need a camera or to see the aurora to enjoy the science and to contribute. If you do see the aurora, you can report it on Aurorasaurus. So I believe that you may have already watched a talk or may be familiar with Aurorasaurus. But if you're not, it's a NASA citizen science project that was founded in 2011 that basically helps answer the question, where in the world is the aurora being seen? And how it works is people can make reports or if not, they have seen the aurora, and those reports get placed on a map along with models of the aurora, which scientists make, which sometimes work, but sometimes don't work. So it's really helpful to have real reports on the ground of the aurora being seen if you're an aurora chaser trying to see the northern lights, because you can look at all these data, you can look at the plots, you can look at graphs, but what's better than having somebody on the ground actually telling you what they're seeing in the sky? That's called ground truth data, and it's being used to validate some of these auroral oval models, like what's called ovation, to better understand how well we're doing at modeling the aurora and modeling the response of space weather in Earth's magnetic system. And so even if you're not, seeing the aurora actively, you can always say, I'm not seeing the aurora. But it's a great way to become involved. If you see the aurora in your own backyard, we've been seeing a lot more space weather now. We're in solar maximum. Chances are we're going to get another one of these big storms like we saw in May and October. And you can go on aurorasource.org. You can submit your photo and your report, and that gets used for science. And it's been used in many studies and to help us better understand how space weather affects our planet. And all of you could become ambassadors to promote aurora citizen science in your community. So understanding sort of, not only to get great information about these different types of auroras, but better understand sort of the needs of the scientific community and how people can contribute and stay up to date with all the great efforts that Aurorasaurus is doing. Aurorasaurus also has a lot of, I should mention too, Aurorasaurus also has a lot of great educator resources, like 3D printed models of Earth's magnetosphere. They have a sort of virtual aurora chase. And Aurorasaurus is just one of many citizen science projects out there. NASA, NSF, they have a lot of different projects that focus on many aspects of space physics, not just the aurora. You can see Aurorasaurus down here, but there's also the GLOBE project, Sun Grazer, so looking at comets diving towards the sun and picking those out and tracking how they move and they're affected, how the solar wind actually affects the comet's tails. The Ham Radio project, HamSci, lots of different ways that people can get involved, even without ever seeing an aurora, classifying different images, all sorts of things. And so you can also teach your library patrons about aurora science. There's many different resources out there. One that I actually created for the Infiniscope project is this thing that I like to call thinking like an aurora scientist. So oftentimes in aurora science, what we're doing is looking at images of the aurora and just characterizing their basic qualities. So for example, what color is the aurora? Where is it being seen in the sky? What kind of shapes are we seeing? So I did this activity with grade schoolers, and it's very simple. Just kind of flashing up images of the aurora and asking people what they're seeing. And then, it's the obvious, right? It's green. It's the winter time. It's a clear sky. The aurora looks like it's in a pattern, like stripes. And then after people go through that activity, kind of revealing, and I have my own sort of responses here, but sort of revealing what a scientist, quote unquote, what a scientist would say. And I mean, the punchline is that, a scientist is going to make the same conclusions as an everyday person. it's actually not it's not anything special. I think everybody can do this, and I think that's the beauty of it, is that a lot of it is just looking at our natural world and writing down what we observe. It's a very pure form of observational science, and that's why I love watching the aurora, because you could be out underneath the aurora and just record notes, and that's scientifically valuable. So I have this resource that I created. There's other resources as well on the clearinghouse. So if you, and all of these are going to be linked on a web page, which I'll share the URL with you all in a little bit. But there's these resources here, these activities you can do, the Earth's magnetic field, living in a bubble, and magnetoplanets. So not just the Earth has a magnetosphere, Jupiter, Saturn, Mercury, Uranus, and Neptune also have magnetic fields and create their own protective magnetic bubbles, which create their own auroras as well. So it's not just the Earth, which has a magnetic field. It extends to other planets as well. And it's interesting knowing about the planets that don't have magnetic fields and how that affects them. So a fun fact is that Mars does not have an intrinsic magnetic field like Earth does. It may have at one point, but because it lost its magnetosphere, the solar wind has slowly stripped away its atmosphere to the point where maybe in a couple billion years it will have no atmosphere at all. So, and because of that, there's radiation on Mars's surface that makes it challenging for humans to potentially, inhabit that planet. So, having a protective magnetic bubble around a planet is a really, positive sign for potential life on its surface. And up at the University of Alaska Fairbanks, we have this Museum of the North. And, I was thinking about, when I was creating this presentation, some really cool, like, hands-on activities that you may want to do with people who visit. And, I was like, okay, well, what can you do? I'm studying these auroral beads. Maybe you can make, an aurora necklace or something. But, I stumbled upon all these great lesson plans with the Museum of the North. So I just, I was like, these guys are doing it way better than I ever could. And there's a lot of really fun things you can do, including just two I listed here: make an aurora bracelet and a watercolor aurora sky. And I think, these are great hands-on activities. People love hands-on activities. I think it's a great way to learn science, is to actually kind of get your hands dirty with it. And not just these two, but you can, do aurora chalk art. Right now, I mean, in Fairbanks, you can't do that because there's snow on the ground. But if you're in somewhere that doesn't have a minus 40-degree winter, that's maybe more applicable. Just exploring magnets, I think, is really beneficial. Getting kids to play with bar magnets and feeling the attractive and repulsive forces. Everything in space is magnetic. The Earth obviously has this giant bar magnet that creates this protective bubble around itself, which is why the solar wind doesn't just go right to the surface and cause damage. But every particle that's flowing in that solar wind has its own magnetic field as well, and that wind is magnetized. It's a plasma. So, teaching about the magnetic forces is, I think, really important, and it's also fun too, just to kind of hands-on, play with magnets. You can also paint the aurora with ice cubes. I can't remember the specifics on that one, but it was interesting. You can pack a Northern Lights backpack. I like to do this too. Is like, if you're gearing up for an aurora chase, what are you going to bring with you, right? You're going to bring your camera. You're going to bring a headlamp. You're going to bring snacks and water. Maybe you're going to bring your phone and pull out the Aurorasaurus app, right? Planning a virtual field trip to see the aurora, I think, is a really fun activity. And yeah, speaking of virtual field trips, Aurorasaurus has this. I actually mentioned this before, but you can take your class, you can take your group that you're presenting to on an aurora chase, and it's kind of like this VR, virtual reality / augmented reality experience, where you can start in your hotel room or start in your bedroom. You can look at the data. So this is showing the auroral power, which is something that Aurorasaurus uses to measure the strength of the aurora. It's a really nice metric because it's just higher equals better. So you can take your participants, your group, on a virtual field trip, get in the car, scout out a clear location. Hopefully you're underneath the auroral oval, or the activity is really good. You can drive to like an open field like this and get a nice view of the northern or southern sky for in the southern hemisphere, right, for the southern lights. And yeah, it's a great activity. I've used it before, and actually I've used it in VR. So if you have access to a VR headset, it's actually really cool. And so, nearing the end of my talk here, but if you're interested in any of these resources and more, have this website set up. It's just the auroraguy.com/pages/aurora dash education, which has all these resources I just talked about, plus even more. So not just these lesson plans and activities, but also sort of kid friendly and public friendly, pages that explain a lot of these auroral phenomena. I think it's honestly pretty hard to find nowadays. You either get stuff that's way too advanced and that people just get lost reading, or it's so simple that it's not actually factual. So I have a few sites on there, and Aurora Source has a really great list of blog articles that are super interesting and also written for a more general audience. But I have everything listed on this site, theauroraguy.com. So yeah, aptly named, aptly named there. So yeah, go and check it out. And with that, I'll take any questions that might have popped up. And thank you for your attention.
Awesome. Thank you so much, Vincent.
Hmm.
Um, Super cool stuff. I'm so jealous of the over half of the folks here have seen an aurora before, and I
Oh,
have
that's
not.
great. Okay.
So I need to, it's part of my bucket list. Lots of thank yous and awesomes in the chat. I'm just scrolling back to see if there are any questions. Um, it looks like there was a question about citizen science.
Yeah.
Is there a minimum age to get involved in citizen science projects?
I I don't think so. Yeah, I'm thinking about it now. I mean, I guess maybe minimum age, like as long as they can read. I think. I mean,
Mhm.
not even that. I mean, the thing is too is like, okay, in Fairbanks, I run like Aurora tours and Aurora workshops, and we get babies and infants and toddlers all the time. And you'd be surprised at the level and like the level of knowledge they have about our natural world. I think that that's one of the first skills that develops is just an ability to point to things and ask. So I don't think that there is a minimum age. I think anybody can do it in some sort of capacity. Yeah, I think that's one of the beauties of citizen science is that it really is all inclusive.
Yeah, and I just add, with my experience with citizen science, I think it's really project specific.
Yeah.
So there's some projects where you're collecting data in a way that you probably need the motor skills of someone a little
Yeah.
bit
Yeah. Yeah.
older,
Yeah.
but then
Yeah.
there's absolutely, I know like iNaturalist, they do bio blitzes, which is just
Yep.
counting species, and I have a 3-year-old
Yep.
son and he loves to go out and point to every single different type of animal or plant that he sees, so I
Hmm.
think it's really project specific. And Tina in the chat said Zooniverse asked for parents' permission to create an account
Okay.
for under 16. So yeah, I think
Okay.
if it's online, absolutely there's
Yeah.
parental
Yeah.
permission
Yeah.
for minors, but there's so many citizen science projects out there. And someone also in the chat had mentioned SciStarter.
Yep.
They have
Hmm.
an incredible library of projects that if you go to their website, you can search by age if you're trying to do something with your kiddos or the youth in your
Hmm.
library. So yeah, lots of different resources out there to get involved, but it's super
Hmm.
fun and just a great way to um, make an impact, in your
Yeah.
community. Great.
I
Any
think too. Oh, I was just going to say, I think too, I was just thinking about it, and something that just popped into my mind is just, I think right now, especially 2024, 2025, is a really relevant time to be talking about the Aurora because the Aurora is the most popular it has ever been in the history. Well, I don't know this for sure, but I'm assuming that history of humankind. If you look at, and I've done this, you can actually look at the data. The word the search term Aurora Borealis has never been searched more than it has been in 2024 throughout the history of the internet, at least. So um, it's pretty cool. I mean, the chances that somebody has seen the aurora, and I've had conversations with, just random people when I've been traveling and stuff, and I'll say that I'm studying the aurora, and they'll say, "Oh yeah, I saw that last month." I mean, that never happened to me before May, before this year. So I think it's really cool. You'd be surprised. I think people have like a shared experience now seeing the aurora that they didn't have before 2024.
Absolutely. Yeah, I there's been moments I've been in places in May, I was in Utah for a conference and I was like, oh, if I had a car, I would drive up into the mountains. Like I saw people in around Salt Lake City posting
Uh-huh.
photos and I just didn't have access to get into a dark sky area. But if another one comes, I'll be prepared.
Yeah, and that's the thing too, is Solar Max is not over. And even not at Solar Max, it is possible to get these extreme events where auroras could be seen all over the US and around the world. So it's definitely not over. If you missed it, it's even, more of an opportunity to get these people involved because because now you know, they're going to be mad that they didn't see it or, they're going to be wanting to learn more. So, yeah,
Awesome. Yeah, and it looks like this audience here has a lot of familiarity with citizen science. Dolores
great.
said at their library they have checkout kits for citizen science with adaptable activities.
Wow.
Um, that is fantastic. And also this spring they're having a citizen science event in their STEM program. So maybe there's something you can do around auroras to add to that event.
That's pretty
Um,
cool.
awesome. Yeah. Any more questions for Vincent or sharing of ideas? We love to steal ideas from each other for our STEM programming. Great. Well, thank you so much, Vincent. I really appreciate you being here and sharing your
Of
story,
course.
your amazing photos and visualizations. And it's really great to have that list of activities that libraries can
Hmm.
go and do in their library. So beyond just learning a lot from a really cool just experience in science, you've left them with a lot of tangible resources that they can utilize in their library program. So we really appreciate that. And thanks. Yeah, Vincent just put the link in the chat. If you're watching the recording, I will be putting that link, the auroraguy.com/pages/aurora-education in the description of the recording. And yeah, thanks, Tina. This has been a really fun series. We really don't do things like this often, so it's been really fun. We will actually have one more in the new year, one more heliophysics presentation. It has not been scheduled yet, but it will be at the end of January. So just check back on the StarNet webinar page. We'll also be putting it out in our newsletter, on our social media. We'll be putting a promotional push. So we will have one more of this series. And we just are just so glad that we have the opportunity to share this expertise with our library friends. So thanks a lot, everybody, and I hope you have a great rest of your day.